Alright guys, so I'm going to go over the notes, the strengths of the acids and bases and start the titrations. Alright, so that way that I could clarify anything that you guys may have and at least give you a deeper understanding of this whole topic all in all. Alright, so when we're talking about strong acids, alright, strong acids are basically any substance, or an acid really, that completely dissociates in water. And so what we mean by that, it completely breaks up. So anytime you have an acid, or strong acid, when it dissolves in water, it breaks up. So like for example, if we want to think about it from a chemical reaction point of view, alright, and what we mean by that, if you have hydrochloric acid, right, and you were to put this in water, you were to dissolve hydrochloric acid in water, alright, what's going to happen? Hydrochloric acid is going to completely dissociate, or 100% dissociate. This simply means that it's going to break up to its individual ions. So you have hydrogen plus and chlorine minus, alright, and so that's what it means by it will break up completely. Or another example, like let's say we have HNO3. Alright, so nitric acid. So nitric acid in water is going to break up to its hydrogen ions plus its nitrate ion. Alright, so since nitrates are polyatomic, that typically stays together. So that's what it will look like. That's the dissociation. Here's another example. If we're talking about sulfuric acid, alright, sulfuric acid is also a strong acid, alright, and so that means when it breaks up, it's going to break up to its to the respective ions, and it will do that 100%. So this reaction is going to be derived all the way to the right, so it's going to be 2H plus SO4 negative 2. Alright, so that's what we mean by it's going to dissociate completely 100%. It's going to break apart, much like how solids or certain salts, when they dissolve in water, they break up to its ion, prospective ions. It's the same thing with strong acids. It's going to break up to its prospective ions. Alright, which differs with weak acids, and with weak acids, they don't typically break up, or most of it won't break up. Alright, so like for example, if you have here, this is acetic acid. And we'll talk about this more next year when we talk about equilibrium and stuff like that. But here's acetic acid. Alright. And so we'll have this equilibrium arrow. That means it could go both left and right. And then you will have H plus C2H3O2. So that's acetate. But what you'll find is that you will have most of this, alright, because most of it won't break up, but some of it will. Alright, and so you will have some small concentration of the ion version of the acid. Alright, and so basically, and this is what the illustration is really kind of showing here, is that here on this side you have a strong acids. So here you have the H that represents just the hydrogen ion, the A represents the other side, but if you look in this solution, they're all broken up. Alright, so 100%. While for the weak acids, alright, if you notice when he says HA, that's just the acid still bonded together. Alright, and so if you want to compare it to what I wrote here earlier, this is your HA, this is the H plus the A. Alright, and so if you were just to kind of compare, to be able to compare and contrast, so the weak acids, if you notice, most of it is still the HA, is still in this form, and then but you have some small percentage, some small concentration that will actually break up to its ion version. Okay, so that's what we mean by strong acids and strong bases. Strong acids and weak acids. Alright, here's just another illustration trying to show this point here, is that here you have your acid. All right, so this is your acid all connected. You're about to dissolve in water. When you dissolve it in water, hopefully you notice that all the circles, the which is just the A, and the hydrogens, which is the purple smaller dots, they're separated out. So once again, and a strong acid, and even strong bases, they're both the same way. They will completely dissociate, completely break apart in water. All right, versus if you're talking about a weak acid and a weak base. All right, if you look at this, you'll notice that most of them are still together. Okay, and you just have some of the hydrogens, some of the acids actually dissociate themselves out. So it's a small percentage. I'm trying to capture them all, but yeah. No, I think this one too. Well, but if you notice, there are some of the acids that kind of dissociate, but majority will stay together. So that's just kind of the point of all this. So weak acids, weak bases, they don't break easily. All right, and so here's just another illustration, just trying to relay that point. All right, strong bases. All right, same idea. As for strong bases, it's mostly your group 1, group 2 hydroxides. So if you look at the periodic table, the lithium, group 1s, we're talking about lithium, sodium, rubidium, francium. These are your group 1 hydroxides, so they're considered strongs. So same idea. If they were to, so let's just talk about lithium hydroxide. If you were to dissolve it in water, it will completely dissociate. So you have lithium plus hydroxide minus. All right, and it's a one-way reaction, and that's the only way it's gonna go. Group 2 hydroxides are the same way. So for example, we have barium hydroxide, which is a group 2 metal. All right, and so it will break up to barium plus 2 hydroxides. Okay, so that's just kind of the big thing on that one. Now, just some of the physical characteristics of strong acids and strong bases. Strong acids and strong bases, because they 100% dissociate, or they completely ionize, they will conduct electricity. All right, so if you were to put some type of electrical probe in here, you put some type of electrical probe in there to test conductivity, you'll see it conducts electricity really, really well. And that's true for both. And weak acids and weak bases, that's not necessarily the case, because they do not dissociate really well. All right, and so because they do not dissociate really well, they're not a strong electrolyte, and so you may not really see, it may not conduct electricity all that well. All right. So let's just kind of talk about acid-base neutralization. Sorry, but when I try to convert this PowerPoint to this program I'm using here, I think a lot of the arrows disappeared and they became boxes. So here, these are just really arrows, and hopefully you can see this. But anytime you mix an acid and base, you make salt and water. All right, bottom line. So here's just an example: hydrochloric acid, all right, with sodium hydroxide. This is a base. All right, so anything with an OH kind of, it's a telltale sign it's a base. What's going to happen is you're going to create water and NaCl. This is a salt. Okay, so NaCl is your salt. So acid plus a base will result in a water plus some salt. Okay, that's just kind of bottom line to it. Now, when we talk about buffers, buffers are basically any system that helps resist pH. Okay, and so the way you typically make them is that you'll take a weak base, all right, and you mix it with its conjugate acid. All right, and so hopefully you just review how we determine conjugate acids and conjugate base. All right, but that's how they're formed. So it's a solution of a weak base with its conjugate acid, or it's a solution with a conjugate acid with its weak base. It's a weak acid with its conjugate base. All right. And so buffers all together, I mean, those systems are used to hopefully to resist large changes of pH, and that's simply because when you add a new substance, all right, if you're adding more H's, okay, either the weak base or the conjugate acid, or the weak acid and this conjugate base is going to eat up the extra hydrogen, so that way the pH doesn't change much. All right, so like for example, a good biological example is your blood. Your blood is a buffer system. It resists pH changes to a certain extent. All right, so that's just the big thing about buffers. All right, so titrations, they're used for us to test concentrations of acids and bases. All right, and so depending what type of acids and base you have, like if it's a strong acid, strong base, weak acid, weak base, you could actually create a titration curve, and you could actually figure out what is the concentration of the other substance if one of them are known. All right, so in your known solution, your known concentration, we call that a standard solution. All right, and so we did this in class. You see exactly how it's kind of set up. You have the burette. What's in the flask is what we call the analyte. All right, and so usually it's called the analyte. What's in the burette, we call it a titrant. Okay, and so this is a titration, and so that's why with the burette, you're able to calculate how much of the titrant was used to neutralize the analyte. Okay, which leads us to titration curves. All right, so there's 3 parts to a titration curve. So this first part here, all right, is basically the pH before you reach the equivalence point. Okay, so in this case here, we're titrating an acid to a base, and how do I know that? The pH starts off high, so we know this is a base. What's in the analyte is the base. All right, and then so what's in your burette is the acid, and so you're adding acid to the base, the pH will begin to drop. Okay, and so it will drop. So here they're usually at 0.1. That's kind of like your little buffer system here. All right, so you're adding the acid, and not much of the pH changes. All right, but once you get to the dead center of this drop, so eventually it's going to drop. All right, so you see this huge spike in pH, difference in pH. Either it drops or increases depending on what's the analyte, what's the titrant. But at the center of this is what we call the equivalence point, and the equivalence point is where you have some equal concentrations. So for strong acids and strong bases, your amount of hydronium, the concentration of hydronium, is equal to the concentration of hydroxide. Okay, and then after that point, you just have excess. A lot more, in this case, a lot more acid, simply because you're titrating an acid to a base. If you flip it, then you're titrating a base to an acid. All right, but the most important thing that you really want to keep note of is this equivalence point, because it actually tells you what substance you're using, what are you titrating. Okay, so like for example, when you're titrating a strong acid to a strong base or vice versa, the equivalence point is always at 7. Alright, the equivalence point is always at 7. So when you see a titration curve that looks like this, and you see the drop, and you look at and you calculate the middle of this drop here. Alright, so when I'm talking about this drop, is this drop here. When you calculate the middle of the drop and you see that the center of the drop is at 7, then you know you have titrating a strong acid with a strong base. Okay, now as I said, it just kind of depends on which direction. So like for this case, the one on the left, the strong acid is titrated with the strong base. So the strong acid is your analyte, your strong base was the titrant, and so you added the base to the acid. While here on this side, it's a strong base titrated with a strong acid. So the analyte here was the strong acid, so that's the original pH. All right, and then you added an analyte's a strong base, and you added a strong acid to it, so that's why you see a drop of pH. I'm trying to make sure I'm not confusing myself here. All right, and so that's that. Here, this is this is a titration of a strong base with a weak acid. And how I know this is a strong base? Well, if you look at the equivalence point, so here's your drop, right? So your drop is here, okay? And you look at the center of the equivalence point, right? You notice that the center of the equivalence point is above 7. So here's 7, here's the equivalence point. So I'm going to call this EP. It's above 7. So if it's above 7, this is your range where the pH is typically basic. And so if your equivalence point is in the basic range, then you know that the strong was the base, all right? And then you had a weak acid. So that's how you could tell. While vice versa, if your equivalence point is below, so here's your equivalence point, and it's below, so here's 7, and it's below 7, then you know you have a strong acid titrated with a weak base. Alright, and so that's the difference, and make sure you are able to identify that. Just know that I will test you on it definitely, but make sure that when you look at a titration curve, always pay attention to the equivalence point and where it lands. So if the equivalence point is above 7, then you know that you had a strong base with a weak acid. If the equivalence point is lower than 7, then you know you had a strong acid that was titrated with a weak base. Alright, so that's just kind of the big thing there. Alright, and so here we're just talking about more of titrations in itself. Oftentimes with titrations, you use some type of indicator, just like the one we did in the lab. It kind of shows you, at least the indicator we used was phenolphthalein, and it shows you when you reach that equivalence point. All right, and so, as I said, indicators are used to help you visually see the pH changes. So that's just one big thing on that one. Alright, so when it comes to calculating using titrations, especially for the ones for strong acids, strong bases, that's the only one that we're really going to talk about. We're not going to look at calculating pHs or titration changes of when you're titrating the strongs and with the weaks, or the weaks and the weaks. All right, that's just, it gets complicated, but we're just going to look at strong acids and strong bases. All right, so with this one, we'll simply use this equation here. All right, so AMAVA equals BMBVB, where the A represents the moles of the acid. So this you will find using the stoichiometry equation. Alright, so looking at the coefficients of the equation, MA represents the molarity of the acid, VA represents the volume of the acid. Alright, B, alright, is basically the moles of the base. So this is found from the coefficients of the stoichiometry of the equation, chemical equation. So from the balanced chemical equation, MB is the molarity of the base, VB is the volume of the base. Alright, so let's go through just a couple of examples so that we can see exactly how this all works out, this all pans out. Alright, so look at this first example here, and I'm trying to straighten this. Alright, whatever. Alright, so first example is, what is the, oops, I meant to use the highlighter. Alright, so the first example is, what is the concentration of HCl if 30 mils of a 0.10 molar of NaOH neutralizes 50 mils of HCl? Alright, and so here's the equation that's given to you. Once again, this is supposed to be an arrow. Alright, here's the equation. Alright, and so what you're going to need to do is use the MAVA equals BMBVB. Alright, and so let's just kind of write out to see what we have. So you need to make sure your equations are balanced. In this case, the equation is balanced. Alright, and now we know that so A represents your acids, your B's always represents your base. Alright, so we want to make sure that we figure out all of this. Alright, so A, MA, VA, B, MB, VB. Alright, so your A is your acid, HCl is your acid, hydrochloric acid. What's my A? It's 1. Ma, so let's look at the problem to see what we can find Ma. And it says that what is the concentration of HCl? So that means that's what we're looking for. That's my X. And my VA, so I'm looking for the volume. So it says what is the concentration of HCl if 30 mils of a 0.10 mole of NaOH neutralizes 50 mils of HCl. So that's my volume of VA. B is my base. So what's my coefficient of my base is 1. MB, I'm looking for the concentration of my base, and so it's 0.10 molar of NaOH. And then VB is the volume of my base, and I tell you that it's 30. Alright, so now all I really have to do is solve for X. Alright, and so when you put write this out and for the equation, you basically have, alright, 1 times MA times 50 equals 1 times 0.1 times 30. Alright, and so if you look at this in the sense of A times MA times VA equals B times MB times VB. Alright, so it's just me substituting the numbers where they belong. And then so all you have to do after that, I'm just kind of scroll this up, and I know I'm moving on to the next slide, but it is what it is. Then all you have to do is solve for MA. And so in this case, if you were to rewrite this, so MA is equal to, you have 1 times 0.1 times 30 over, which is really 50 times 1, and I'll kind of put this in parentheses. Alright, and so when you solve for this, you will get the answer for MA. And so what you should get is 0.06 molar. So the concentration of the acid of HCl is 0.06. Okay? Alright, so let's look at the next example here. Alright, so the next example, we have 20 mils of solution of strontium hydroxide is neutralized, and after 25 mils of standard solution, 0.05 molar solution is HCl is added. What is the concentration of strontium hydroxide? So once again, kind of list out to the side alright, the things that you're going to need. Okay, so for my A is my acid, alright, and so this is my acid, that's my coefficient, so it's 2. Molarity of my acid, so if you look, it says 20 mils of solution of strontium hydroxide is neutralized after 25 mils of a standard 0.05 molar HCl, so it's 0.05. And the volume is 25 mils. Alright, so make sure you read the question so you understand what's going on here. Alright, now for B, it's my coefficient of my base. Here's my base, so my coefficient here is 1. My molarity is asking what is the concentration of strontium hydroxide, so that's my X. And what is the volume? Well, it says 20 mils of the solution, so that's my volume, 20 mils. Alright, so when I write this out, it's basically 2 times 0.05, I'm just use access times 25 equals 1 times X, alright, times 20.0. Alright, so if you substitute to find what MB is, right, I'll rearrange this equation. So MB essentially will be 2 times 0.05 times 25 divided by 20 times 1. Alright, and so this is basically the setup for this one. So MB, well, alright, so the concentration of the base, when you put this in the calculator, you'll get 0.125 molar. Alright, and so the concentration of your strontium hydroxide is 0.125. Alright, so let's look at this third example here. Alright, so how many mils of 0.20 molar of H3PO4 are needed to neutralize 55.0 mils of a 0.10 molar solution of NaOH? Alright, I can already tell you this. This is a really bad example because it's not using a strong acid. But let's just pretend this is a strong acid just for the sake of the math itself. Alright. But it has a strong base. But let's just, as I said, let's pretend. But the first thing you need to do, you need to write out the chemical equation. Alright. So you have H3PO4 plus NaOH. And you always make water plus a salt. So here's sodium phosphate, so it's Na3PO4. Alright, so hopefully you remember how to write chemical equations here. Alright, and then this needs to be balanced. Alright, so to balance this quickly, so this will have a 3 in front of it. Let me see, 6, 6, 2, oh, and this will need a 3 as well. Alright, so I'm trying to make sure. So this will give me 6 hydrogens, 3 hydrogens plus 3 hydrogens, 6. We have 4 plus 7, 3, 7. Yes, so this is your balanced chemical equation. Cool. Alright, now, so let's figure out what is our A, MA, and VA. I apologize if you hear my kids in the background. B, MB, VB. Alright? And so your acid, you're looking for the coefficient of the acid, which is here, phosphoric acid. It's just 1. The concentration of your acid, and so here it's really just 0.20, sorry. And then the volume was just how many milliliters you need. So that's what you're looking for. And then for your base, you need the coefficient of your base here, so it's a 3. The concentration of the base, which is 0.1. And then finally the volume of the base, which is 55. Alright, so you need to make sure you kind of read this out so you know what's what. Alright, and so basically this is 1 times 0.2 times VA equals 3 times 0.1 times 55. So if we solve for VA, we get 3 times 0.1 times 55 over 1 times 0.2. Alright, and so that's basically the setup for VA to find the volume of the phosphoric acid. Alright, and so when you put this in the calculator, you'll get, alright, so I got 82.5 milliliters. Okay, so that's this problem here. And then last but not least, same issue, they use the weak acid, but regardless, let's just do the math for the sake of the math. Alright, so what's the volume of a 0.20 molar of calcium hydroxide will neutralize 45.0 milliliters of 1 molar of solution of HClO3? Alright, so once again you need a chemical equation. So the chemical equation is, you have calcium hydroxide plus HClO3. You remember, anytime you mix an acid with a base, you always make water. Alright, and then you have to just basically combine the salts here. So this is going to react with this. That's your water. Ca is going to bond with this. So you just got to remember your charges. So it's calcium ClO3 2, because chlorate has a -1 charge. Alright, so that's this, and then you just got to make sure it is balanced. So I know already I need 2 more chlorates because of this here, and so that makes it, I have 4 hydrogens, so I will need a 2 here. Alright, so 4 hydrogens, that makes it 2, 6, 8, 6, 8. Alright, oxygens, perfect. So this is a balanced chemical equation. So it's 1, 2, 2, 1. Alright, and so now let me figure out my values for VA, A, and MA, and my values for B, VB, and MB. Okay, so for my A, This is my acid, so it's 2. What's the volume for A? Well, let's just read the question. It says, what is the volume of CaOH2 will neutralize 45 mils of a 1 molar solution of HCl3? So this is my volume, 45 mils. And my concentration is 1. Okay? Now for my base, here it's 1. Volume, it says what is the volume, so that's what I'm looking for, and the concentration is 0.2. Alright, so if I write this up, set this up accordingly to the equation, then we know that it is 2 times 45 times 1 is equal to 1 times VB times 0.20. Alright, so I'm going to go ahead and solve for VB. So by solving for VB, I have 2 times 45 times 1 over 1 times 0.20. Alright, and so when you put this in the calculator, you'll get, alright, and then I got, so VB is equal to 450 mils of your calcium hydroxide. Alright, so that's that.